Alright, welcome to this new video. Focus on the eigenspace. So basically we have to define the concept of the eigenspace and also apply. Take one example and see how to show that the set is an eigenspace, okay? So let's consider, by definition, the set E lambda is defined as V vectors, okay, in Rn such that A, the matrix, times V is equal lambda V is called the eigenspace of the matrix A with the corresponding eigenvalue lambda if the following three conditions are satisfied. 1. We have to show that the zero vector belongs to E lambda. So this means it is not empty, even though the zero vector is not part of the eigenvalue. Right. The second and the third step, I can put it under these two and say that E lambda is subspace of Rn. Okay. For the steps, subspace requires two steps. The first step is to show that it is closed under vector addition, and the second step is to show that it's closed under scalar multiplication. So for the vector addition, we let U and V, two vectors in E lambda. Okay, we want to show that AU plus V is equal AU plus AV. Vector, vector. This is equal lambda U plus lambda V. This is lambda bracket U plus V. Then conclusion, this is closed under vector addition. Alright, for the second step, we let U in E lambda and alpha is a scalar. If you multiply this, AU is equal alpha times lambda U. Alright, here we can put alpha since it's a constant in front. This becomes alpha U, and this means that it is closed under scalar multiplication. So these are the main three steps. If you want to show that it is an eigenspace, you have to show first of all that it's non-empty, and secondly you have to show that it's closed under vector addition, and third step you have to show that it is closed under scalar multiplication. Alright, with this, the next question is, what is the dimension of an eigenspace? Okay, by definition, the dimension of the eigenspace E lambda is the geometric multiplicity of the corresponding eigenvalue lambda. What does it mean? It means that the geometric multiplication is always greater or equal to 1. So geometric multiplication, and this is also less or equal to the algebraic multiplication, and this is less or equal to the dimensions of the matrix. Okay, so every time we have to make sure that this condition is satisfied for the geometric multiplicity or even the algebraic multiplicity. Okay, if the geometric multiplicity is equal to algebraic multiplicity for all eigenvalue of our matrix, then we say in this case that the matrix is diagonalizable. But this is the next topic, so we will discuss in detail and you'll be able to get from there. This is an example where you want to show that this is an eigenspace, okay? So basically here you consider an n by n matrix A with the eigenvalue lambda. And the question is, can we prove that this is an eigenspace corresponding to the eigenvalue lambda in a subspace Rn? Yes, we can do that. It just requires 3 steps to complete. The first step, as I mentioned in the video, is to show that it is not empty. So it means the 0 vector belongs to this eigenspace. Secondly, you want to prove the vector addition. You want to prove that it's closed under a vector addition. And lastly, we have to show that it is closed under scalar multiplication. Okay, so let's do it quickly. First step, non-empty. Non-empty. All right, to show that it's non-empty, we just have to say that the 0 vector belongs to the eigenspace lambda. Okay, the 0 vector belongs to the eigenspace lambda. For vector addition, if we let u and v all belong to the eigenspace lambda, okay, then by definition a times u is equal lambda u. Also, a times v is equal lambda v. If we sum up these two lines, then we have a bracket u plus v is equal lambda bracket u plus v. Okay, then we prove that if lambda, u, and v belong to this eigenspace E lambda, then u plus v also belong to E lambda. And this is all for the vector addition. Now for the scalar multiplication, okay, we let u also belong to the eigenspace E lambda, and we take some scalar alpha, some scalar, okay? Then by definition, u, a times u is equal lambda u. If we multiply this by the constant lambda, the scalar lambda, we have alpha times a u is equal alpha lambda u. Right, this is a scalar, so we can change the position. This become a times alpha u is equal lambda alpha u. So this clearly means that alpha u also belong to lambda, the eigenspace E lambda. So this is all. It's very simple, but you have to respect all these 3 steps in order to show that eigenspace corresponds to the subspace here. Okay, so that's all for this video. Thank you.